Hey, today I'm going to go take a look at what might be one of the most intense casework problems I've ever seen in a mathleague.org test. It's about counting edges in a regular decagon that are colored red, green, or blue. But before all this casework, I'm going to go analyze this problem statement a bit more carefully so I can make sure that I'm doing my casework right. And to do this, I'm going to go use my handy dandy mathematical model so I can model out this decagon and its conditions. Okay, so the first condition is that each edge has at least one neighboring edge of the same color. So as an example, this blue sandwiched between two reds does not count because this blue does not have a neighboring edge that is also blue. The second condition is that rotations of the same coloring are considered identical. So if you set up the one possible decagon coloring as this, and then let's say you decide to swap this piece with this piece like this, then that does not count as a new coloring because then you can rotate the entire thing to get basically the same thing in terms of color. So with this in mind, let's list out the casework. Casework based on the number of continuous runs of colors, which I'll call streaks. And I'm going to go do a little T-table-like thing just to make it a lot easier to keep track of all this information, because there is a lot. The one streak case is going to be fairly straightforward, 10. The two streak case, we're not going to include 9-1 because the 1 is going to violate one of the conditions, but we will include 8-2, 7-3, 6-4, and 5-5. The three streak case, after some trial and stuff, we can find that the 6-2-2 case, 5-3-2 case, 4-4-2 case, and 4-3-3 case all work. How about the 4-streak case? Well, we have 4-2-2-2, and we also have 3-3-2-2 and 3-2-3-2. And then we have the 5-streak case, which is just 2-2-2-2-2. And we also know that we won't have 6 or more streak cases because then this would result in one color just being by itself and its edges being different colors. So that will not satisfy one of the conditions. Okay. So the 10 case, 3 colors, 3 ways, simple as that. The 8-2, 7-3, and 6-4 cases, 3 ways to pick one of the colors and then 2 ways to pick after that. 3 times 2 is 6 cases each. But 5-5, because of some rotational symmetry shenanigans, we have to divide by 2 in order to get 3. The 6-2-2, 4-4-2, 4-3-3 would have to involve all 3 colors, because if there was only 2, then we would essentially be doing the 2-streak case, which we've already done and we don't want to overcount. So 3 ways to pick the first color, 2 ways to pick the next, and then only 1 for the last, so 6. The 5-3-2 case will also be 6 ways each, right? Well, one way we can have the 5-3-2 case is if we have 5 reds followed by 3 blues and then 2 greens, just like this. But hold on a second. What if we swap these 2 greens with these 3 blues? Let's do that. Okay, let's rotate. Check for rotation. Doesn't seem like we're getting the original. Yeah, turns out that this is an entirely new case. The other 6-2-2, 4-4-2, and 4-3-3 do not have that because of the repeating number, but for 5-3-2, that's a different story. So we basically double. Okay, so for the 5-3-2 case, we're going to have 6 times 2 or 12 ways. The case of 4 streaks is the trickiest. We can either use 2 colors or 3 colors. The 2 colors are a lot more straightforward because of the forced alternation and result in 6 ways each from picking 3 for the first one and 2 for the next. So 6 ways each. As for the 3 color subcase, well, we can approach them similarly. And think about the 4 streaks, 3 color strategy. For an example, I'm going to use the 4-2-2-2 case. So let's say we put 4 blues like this, and then a red, 2 reds like this.
we could put 2 greens like this, but then the last one would have to be 2 reds, because if it was 2 blues or 2 greens, then we would end up with something like this, or something like this, where as you'll see, this is a continuous band of 4 rather than 2. Similarly with this one, this is a continuous of 6 and not 4-2. So we must have this. On the flip side, we could have this, where it's blue, then red, then blue, but then the last 2 must be green, because otherwise, if it was red, then it would not have 3 colors. So it must be green. So either way, you have 3 to choose from the first one, red, green, or blue, but then you have 2 for the next one because the first one can't be used, and then 2 again, but either way, the last one is predetermined.
So in summary, this means that for the 3-color subcase, we're going to have 3 times 2 times 2, which is going to be 12. And that's it for the 4-street cases. Wait, hold on a second. I'm looking at the 3 subcase for the 3-2-3-2.
For the 3-2-3-2 case, which is one of the 4-streak subcases, pigeonhole principle means that one of the streaks would have the same color as another streak. Let's have that be blue, the blue as an example with the 2 streaks. So something along the lines like this. Almost there, and done. Let's swap the red and the green pieces. So something like this. But hold on a second. Rotate, rotate, rotate. And we're basically in the same coloring position as before. Yeah, we've basically overcounted this thing. And the overcounting comes from swapping the 2 different color parts. So we're going to have to divide by 2.
So for the 3-2-3-2 case, for the 3-color subcase, we don't have 12 ways. Instead, we have half that, which is going to be 6 ways. And now we are truly done for the 4-street case. Now the last one is the 5-street case. Well, we have to use all 3 colors because of the alternation thing. And one of the colors is going to have to be used once. So there are 3 ways to pick the one color that's used once, and then 2 ways to pick the next color, and then the rest will just result in forced alternation. So this will result in a total of 6 ways. All right, and we're finally done. Let's add them all up. And if you do so, 3 + 6 + 6 + 6 + 3 + 6 + 12 + 6 + 6 + 6 + 12 + 6 + 12 + 6 + 6 + 6, we get a total of 108 ways. And I'm finally done with this problem.
Hi, everybody. This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.